Correction for this chapter. In mathematical formulae, instead of I, hear 1.
Relativity, the Special and General Theory, by Albert Einstein. Continuing Part 1, the Special Theory of Relativity, Sections 10 to 12. Section 10, on the relativity of the conception of distance. Let us consider two particular points on the train, for example the middle of the first and of the 100th carriage, travelling along the embankment with the velocity v, and inquire as to their distance apart. We already know that it is necessary to have a body of reference for the measurement of a distance, with respect to which body the distance can be measured up. It is the simplest plan to use the train itself as reference body, or coordinate system. An observer in the train measures the interval by marking off his measuring rod in a straight line, for example along the floor of the carriage, as many times as is necessary to take him from the one marked point to the other. Then the number which tells us how often the rod has to be laid down is the required distance. It is a different matter when the distance has to be judged from the railway line. Here the following method suggests itself. If we call A' and B' the 2 points on the train whose distance apart is required, then both of these points are moving with the velocity v along the embankment. In the first place, we require to determine the points A and B of the embankment, which are just being passed by the 2 points A' and B' at a particular time t, judged from the embankment. These points A and B on the embankment can be determined by applying the definition of time given in section 8. The distance between these points A and B is then measured by repeated application of the measuring rod along the embankment. A priori, it is by no means certain that this last measurement will supply us with the same result as the first. Thus, the length of the train, as measured from the embankment, may be different from that obtained by measuring in the train itself. This circumstance leads us to a second objection which must be raised against the apparently obvious consideration of section 6. Namely, if the man in the carriage covers the distance w in a unit of time, measured from the train, then this distance, as measured from the embankment, is not necessarily also equal to w. Section 11. The Lorentz transformation. The results of the last 3 sections show that the apparent incompatibility of the law of propagation of light with the principle of relativity, section 7, has been derived by means of a consideration which borrowed 2 unjustifiable hypotheses from classical mechanics. These are as follows. 1. The time interval, or time, between 2 events is independent of the condition of motion of the body of reference. And 2. The space interval, or distance, between 2 points of a rigid body is independent of the condition of motion of the body of reference. If we drop these hypotheses, then the dilemma of section 7 disappears, because the theorem of the addition of velocities derived in section 6 becomes invalid. The possibility presents itself that the law of the propagation of light in vacuo may be compatible with the principle of relativity, and the question arises, how have we to modify the considerations of section 6 in order to remove the apparent disagreement between these 2 fundamental results of experience? This question leads to a general one. In the discussion of section 6, we have to do with places and times relative both to the train and to the embankment. How are we to find the place and time of an event in relation to the train when we know the place and time of the event with respect to the railway embankment? Is there a thinkable answer to this question of such a nature that the law of transmission of light in vacuo does not contradict the principle of relativity? In other words, can we conceive of a relation between place and time of the individual events relative to both reference bodies, such that every ray of light possesses the velocity of transmission c relative to the embankment and relative to the train? This question leads to a quite definite positive answer, and to a perfectly definite transformation law for the space-time magnitudes of an event when changing over from one body of reference to another. Before we deal with this, we shall introduce the following incidental consideration. Up to the present, we have only considered events taking place along the embankment, which had mathematically to assume the function of a straight line. In the manner indicated in section 2, we can imagine this reference body supplemented laterally and in a vertical direction by means of a framework of rods, so that an event which takes place anywhere can be localized with reference to this framework. Similarly, we can imagine the train traveling with the velocity v to be continued across the whole of space, so that every event, no matter how far off it may be, could also be localized with respect to the second framework. Without committing any fundamental error, we can disregard the fact that in reality these frameworks would continually interfere with each other, owing to the impenetrability of solid bodies. In every such framework we imagine three surfaces perpendicular to each other, marked out and designated as coordinate planes or coordinate system. A coordinate system K then corresponds to the embankment, and a coordinate system K' to the train. An event, wherever it may have taken place, would be fixed in space with respect to K by the three perpendiculars x, y, and z on the coordinate planes, and with regard to time by a time value t. Relative to K', the same event would be fixed in respect of space and time by corresponding values x', y', z', and t', which of course are not identical with x, y, z, and t. It has already been set forth in detail how these magnitudes are to be regarded as results of physical measurements. Obviously, our problem can be exactly formulated in the following manner. What are the values x', y', z', and t' of an event with respect to K' when the magnitudes x, y, z, and t of the same event with respect to K are given? The relations must be so chosen that the law of the transmission of light in vacuo is satisfied for one and the same ray of light, and of course for every ray, with respect to K and K'. For the relative orientation in space of the coordinate systems indicated in the diagram, this problem is solved by means of the equations x' equals x minus vt over the square root of I minus v squared over c squared, y' equals y, z' equals z, and t' equals t minus v over c squared times x over the square root of I minus v squared over c squared. This system of equations is known as the Lorentz transformation. Footnote: a simple derivation of the Lorentz transformation is given in Appendix 1. If, in place of the law of transmission of light, we had taken as our basis the tacit assumptions of the older mechanics as to the absolute character of times and lengths, then instead of the above we should have obtained the following equations: x' equals x minus vt, y' equals y, z' equals z, t' equals t. This system of equations is often termed the Galilei transformation. The Galilei transformation can be obtained from the Lorentz transformation by substituting an infinitely large value for the velocity of light c in the latter transformation. Aided by the following illustration, we can readily see that, in accordance with the Lorentz transformation, the law of the transmission of light in vacuo is satisfied both for the reference body K and for the reference body K'. A light signal is sent along the positive x-axis, and this light stimulus advances in accordance with the equation x equals ct, i.e. with the velocity c. According to the equations of the Lorentz transformation, this simple relation between x and t involves a relation between x' and t'. In point of fact, if we substitute for x the value ct in the first and fourth equations of the Lorentz transformation, we obtain x' equals c minus v times t over the square root of I minus v squared over c squared, and t' equals I minus v over c multiplied by t over the square root of I minus v squared over c squared, from which, by division, the expression x' equals ct' immediately follows. If referred to the system K', the propagation of light takes place according to this equation. We thus see that the velocity of transmission relative to the reference body K' is also equal to c. The same result is obtained for rays of light advancing in any other direction whatsoever. Of course, this is not surprising, since the equations of the Lorentz transformation were derived conformably to this point of view. Section 12. The behavior of measuring rods and clocks in motion. Place a meter rod in the x' axis of K' in such a manner that one end, the beginning, coincides with the point x' equals 0, while the other end, the end of the rod, coincides with the point x' equals I. What is the length of the meter rod relatively to the system K? In order to learn this, we need only ask where the beginning of the rod and the end of the rod lie with respect to K at a particular time, t, of the system K. By means of the first equation of the Lorentz transformation, the values of these 2 points at the time t equals 0 can be shown to be x, beginning of rod, equals 0 over the square root of I minus v squared over c squared. X, end of rod, equals I over the square root of I minus v squared over c squared. The distance between the points being the square root of I minus v squared over c squared. But the meter rod is moving with the velocity v relative to k. It therefore follows that the length of a rigid meter rod moving in the direction of its length with a velocity v is the square root of I minus v squared over c squared of a meter. The rigid rod is thus shorter when in motion than when at rest, and the more quickly it is moving, the shorter is the rod. For the velocity v equals c, we should have the square root of I minus v squared over c squared equals 0. And for still greater velocities, the square root becomes imaginary. For this we conclude that, in the theory of relativity, the velocity c plays the part of a limiting velocity, which can neither be reached nor exceeded by any real body. Of course, this feature of the velocity c as a limiting velocity also clearly follows from the equations of the Lorentz transformation, for these become meaningless if we choose values of v greater than c. If, on the contrary, we had considered a meter rod at rest in the x-axis with respect to k, then we should have found that the length of the rod as judged from K' would have been the square root of I minus v squared over c squared. This is quite in accordance with the principle of relativity, which forms the basis of our considerations. A priori, it is quite clear that we must be able to learn something about the physical behavior of measuring rods and clocks from the equations of transformation, for the magnitudes z, y, x, and t are nothing more nor less than the results of measurements obtainable by means of measuring rods and clocks. If we had based our considerations on the Galilean transformation, we should not have obtained a contraction of the rod as a consequence of its motion. Let us now consider a seconds clock, which is permanently situated at the origin, x prime equals 0, of k prime. T prime equals 0 and t prime equals I are two successive ticks of this clock. The first and fourth equations of the Lorentz transformation give for these two ticks t equals 0 and t prime equals I divided by the square root of I minus v squared over c squared. As judged from k, the clock is moving with the velocity v. As judged from this reference body, the time which elapses between two strokes of the clock is not 1 second, but I divided by the square root of I minus v squared over c squared seconds, i.e. a somewhat larger time. As a consequence of its motion, the clock goes more slowly than when at rest. Here also the velocity c plays the part of an unattainable limiting velocity. End of section 12.